Last section in Chapter 10, 10.6, construct and interpret binomial distributions. All right, so you're going to see some funny things. When you're rounding, which you're going to get some really small numbers, just use 2 significant digits. That means like 2 numbers after any zeros. In scientific notation, you're going to see some stuff on the calculator you may be aware of, you may not. Answers that can be so small that the calculator puts them in scientific notation. And this is how the calculator will write it. And this means move the decimal 5 places to the left, which would be like that. 4 places to the left, which would look like that. So just kind of wanted you to be aware of that. Okay, there's 2 types of binomial experiments. The first are when you have a 50-50 probability of things occurring. The requirements to have a binomial experiment is that there are 2 disjoint outcomes. For example, like when you have a win or lose. Those are disjoint, or if you're looking for odds or evens. There's no way they could overlap. All right? And the trials are independent. One event doesn't affect the other. For example, just as a refresher, if you flip a coin 2 times, count the times it lands on heads. And that is independent because the second coin is not affected by what happens. The second toss is not affected by what happens with the first toss. All right, binomial experiment. And this is how the book shows it. For a binomial experiment, the probability of exactly k successes, the number of ways it can happen, in n trials is this. And that's okay. I just wanted to show it to you because that's what's in the book. An easier way to look at it is finding the theoretical probability when odds are 50-50 is use a decimal setup. And this is really basically the same thing that they have up here. I just wrote it in easier words. The probability of success raised to the number of successes you're looking for times the probability of failure raised to the number of failures times n choose k. N is the total number of trials and k is the number of successes. This I will give you for the test. We'll give you for the test. You don't really have to write that down, but just saying, okay? So let's practice this a little bit. We're going to find the theoretical probability, that means we're not conducting an experiment, of getting each, when you toss a fair coin 8 times. So we're going to toss the fair coin 8 times. That means a total flips. Okay? So we want to know the probability of getting exactly 3 heads. These are the number of successes. We want to get heads 3 times. So if I go by what this says here, I can find the probability without actually tossing a coin multiple times and using experimental probability. I can just use this. So the first thing it says is I have to write the probability of success. Well, the probability for getting a heads or tails is 50-50. So the probability for getting a heads is 0.5. And the number of successes I want are 3. This is heads. And then the probability of getting tails, which is failures, is also 0.5. And out of 8 tosses, that means 5 of them are going to be failures and 3 are successes. And then I got to multiply it by 8 choose 3. If I do this math, it'll give me the theoretical probability that this is going to happen. And that ends up equaling 0.22, which is the same as 22%. All right. Now I want to know the theoretical probability of getting at least 7 heads. That means out of the 8 tosses, I want 7 heads or 8 heads. I want to find out the chance of that happening. So you have to do it 2 different times. And since they're disjoint, you're going to add them together. So 7, if I write it first for 7 times, again, there's a 50-50 chance. And I want 7 successes times the 50-50 chance for failure. And I want 1 failure times 8 flips, choose 7 heads. When I do that math, I get 0.031. It's a pretty slim chance of getting 7 heads. But now I have to also do it wanting 8 heads or 8 successes. So again, it's 50-50 chance, 0.5, and I want 8 successes. And then the failures, I want 0 of those, times 8, choose 8. And that is equal to 0.0039, an even smaller chance of getting 8 heads. I add those two together to get the probability of getting 0.035, of getting at least 7 heads, which is a pretty small chance. It's 3.5%. All right, let's try another one. Tony makes 50% of the free throws he shoots. If he shoots 6 free throws, what is the probability that he will make all 6? So my successes would be the shots he made, and failures would be the shots that he misses. So, again, he's got a 50% chance each time. So I want to find out what the theoretical probability is of him making all 6. So I want 6 of them to be made and 0 of them to be missed, times 6 choose 0, 6 choose 6. I want all 6 successes. And when you multiply that, it's 0.016. So it's a pretty slim chance of making all 6 free throws, because if you think about it, it's 1.6%. Let's try another one. Half of the teachers at DHS are married. If you ask 10 teachers to chaperone a dance, what is the probability that exactly 5 are married? Okay, well, since it says half, that means 50-50 chance. 50% are married. So what we need to do is we want our successes to be married. This sounds kind of funny, but our failures to be single. So 50% chance that they're married, and we want all 5 of them. We want the 5 that we choose to be married, which means that the 5 that we don't choose are going to be single. And then we have to multiply that by 10 total, choose 5. That equals 0.25, or a 25% chance that exactly 5 of them will be married out of the 10. Okay, now let's flip it over and see what we have on the back. So, we can use binomial, the theoretical probability equation for binomial experiments when the probability is not 50-50 if, again, they're disjoint and they are independent. And it's the same, really, it is the same theoretical equation here. N is the total number of trials, and K is the number of successes. So here, this is not going to be a 50-50 chance. It says the probability of being left-handed is only 10%. Find the probability that exactly 2 out of 3 students, so this is my total, chosen at random, are left-handed. Well, if I use this equation again, instead of conducting an experiment, I'm just going to use this equation to find this chance. So I know that there's a 10% chance of getting left-handed, and I want to know if I choose out of 3 students that 2 of them will be left-handed. That's my successes here. Then you have to consider, well, that means that there's a 90% chance of failures, and I only want 1 of them to not be left-handed. So this is a 10% chance of left-handed and a 90% chance of right. Then I got to multiply that by 3 total, choose 2. 0.027. So I only have a 2.7% chance that 2 of the 3 students are going to be left-handed, which kind of makes sense because only 10% of the population is left-handed, according to this statement. Let's try a different one. In a certain school, about 20% of the students walk to school. Find the probability that exactly 3 out of 4 students walk to school. Again, I'm guessing it's not going to be very high because only 20% of them do actually walk to school. So let's see the probability. So again, my successes are going to be the walking students. There's a 20% chance that they walk, and I have choose 3 of them. And then the non-walking students, 80% of them don't walk, and I only want 1 of them to fall into that category. Then I got to multiply it by 4 total, choose 3. Again, I'm just taking this purely from this equation. And that equals 0.026, which again is only a 2.6% chance, not very many. All right, let's look at this a little bit differently now for not 50-50. A football team wins 65% of their games. If they will play 8 games next season, so this is my total, what is the probability that they'll win? At least 7. So remember, K is successes, N is trials, and P is the probability of success. So here's what I'm looking. K is greater than or equal to 7. That's how many successes I'm looking for. N is 8, and P is 0.65. That's probability of success. So again, I have to look at it as 2. So I want to find the successes for 7 and 8. So the first one I'll find is for 7 wins. So I have a 0.65% chance of winning, and that's going to be to the 7th. Each game is 65% chance. And then a 0.35 chance of losing. And I only want 1 of my games to be losing. And then I multiply it by 8 total, choose 7, and I get 0.137. Now I need to do it for 8 games as well. Remember, each game I have a 65% chance of winning, so that's going to be to the 8th because I want to win 8 games. And a 35% chance of losing, but I want 0 losses. And then I want 8, choose 8. And that equals 0.32. Add them together, because they're disjoint, and you get 0.169, or approximately 17% chance of winning at least 7 or 8 games. Let's just look at one more like that. According to a survey, about 41% of U.S. households have a soccer ball. Suppose you ask 6 randomly chosen U.S. households whether they have a soccer ball. What is the probability that at most 2 households will have a soccer ball? At most means 0 households, 1 household, or 2 households. That's it. What's the chance of that happening? So again, K equals successes, N is trials, and P is probability of success. We want to know K is less than or equal to 2, and this is the number of trials, and this is the probability. So let's find the successes for 2 households, 1 household, or 0, because we're looking at most 2. So, probability that K is less than or equal to 2 is going to look like this. First, I'll start with 2 households being the 2 households owning a soccer ball. So, successes is 41%, and we want 2 of those. And out of 6 trials, if only 2 of them have soccer balls, that means that 4 houses don't have soccer balls. That's 59%. Times 6, choose 2. And that's 0.3055. Now let's look at if just 1 household has a soccer ball. So only 1 of them have a soccer ball, which means that 5 of them do not. And I want 6, choose only 1. And that's 0.1759. And then let's look at it as if no households had a soccer ball. So that means there's a 0.41 to the 0. 0 successes times 6 failures or no soccer ball. And then that's 6, choose 0, equals 0.0422. And when you add those up, it's a total of 0.5236, which is approximately 52% have at most 2 soccer balls. So again, really all this is about is finding the theoretical probability instead of conducting an experiment and just using this equation for any disjoint, two disjoint events, and that they have to be independent as well. Alrighty? That's it.